2019 AP Physics 1, question number 2. This problem explores how the relative masses of two blocks affect the acceleration of the blocks. Block A, of mass ma, rests on a horizontal tabletop. There is negligible friction between block A and the tabletop. Block B, of mass m, hangs from a light string that runs over a pulley and attaches to block A, as shown above. The pulley has negligible mass and spins with negligible friction about its axle. The blocks are released from rest. A, part I. Suppose the mass of block A is much greater than the mass of block B. Estimate the magnitude of acceleration of the blocks after release. Briefly explain your reasoning without deriving or using equations. Okay, so in this instance, the mass of block A is much greater than the mass of block B. So that means the acceleration of block A would be close to 0. If you include units, meters per second squared. Now we'll explain here. Since the mass of block B is so small, it can be considered negligible. Thus, since block A is much heavier, it won't move due to the force of block B. Now you can also say something along the lines of inertia, how block B's mass is too small, so it won't have enough inertia to move block A. Anything along those lines would work. Now for part 2. Now suppose the mass of block A is much less than the mass of block B. Estimate the magnitude of the acceleration of the blocks after release. So in this instance, it's the opposite of what we just answered. Now block A is much smaller than block B. So if we refer back to our diagram from earlier, we can see that block A is on the table horizontally, while block B goes vertically. So if we think about it, block A, if it's so small, then it's almost like there's nothing there. That means block B will just be hanging. There's no tension, there's nothing holding it up. That means it'll just fall to Earth. That means it'd probably be close to 9.8 meters per second squared, which is acceleration due to g, or gravity. So we can write that here for part 2. We can say close to g, or 9.8 meters per second squared. Now to explain it, we can say if block A is much less than block B, then block A can be considered negligible. Then block B would be almost similar to falling due to gravity, which would mean it would accelerate close to 9.8 meters per second squared. Moving on, part B. Now suppose neither block's mass is much greater than the other, but they are not necessarily equal. The dots below represent block A and block B as indicated by the labels. On each dot, draw and label the forces, not components, exerted on the block after release. Represent each force by distinct arrows starting on and pointing away from the dot. So let's refer back to the diagram to see which forces are acting on it. You can see on block A, it's being pulled towards the right by a tension force. There's force of gravity pointing downward, and that must mean there's a normal force from the surface pointing back up. So this is our quick diagram of block A. Now for block B, you can see that it's hanging due to this cord. That means there's a tension going up. And similarly, since there's gravity, that means there has to be a gravity force pointing downward. Now we have our quick sketch. We just have to draw it back in part B. So remember for block A, there was the force of gravity going downwards. There's also the normal force, which is equal in magnitude, so make sure they're the same length. And then towards the right, there's a tension force of gravity, which is denoted by F subscript of G. And then for block B, similarly, there's the force of gravity going downward, and then there's a tension force going up. There we go. Part C. Derive an equation for the acceleration of the blocks after release in terms of ma, mb, and physical constants as appropriate. If you need to draw anything other than what you have drawn in Part B to assist in your solution, use the space below. Do not add anything to the figure in Part B. So we have to try to derive acceleration. So let's use our free body diagrams to help us determine. And we can use Newton's second law while we're at it. So let's draw a quick sketch of the diagram to remind us of what everything looks like. We have the block here with a tension going this way. And this tension is connected and the same as the tension going upward from the block. So in other words, we have these forces acting in the same direction. The tension from block A, the tension from block B, and the force of gravity from block B. So let's use Newton's second law, which states that the net force is equal to the net mass, which in this case is ma plus mb, times the acceleration which we're looking for. So the net force in this direction, we can see that there's the force of friction going down minus the tension force plus the tension force over here. So we can draw that with Fg minus tension force plus tension force. So we can see that a minus tension plus tension, that would cancel out. So if we expand F of G, which is the force of gravity on block B, that means it's the mass of block B times the gravitational constant G. So mbg is equal to our previous part, mass of A plus mass of B, all times the acceleration. So we can solve for acceleration by dividing ma plus mb from both sides. Get mb times g all over m of A plus m of B. And this is what is equal to our acceleration. Consider the scenario from the second part of A, where the mass of block A is much less than the mass of block B. Does your equation for the acceleration of the blocks from part C agree with your reasoning in the second part of A? Yes or no? So here's our equation from earlier, and it says if the mass of block A is much less than mass of block B. So we can use this equation and see that if mass of A here goes to 0 since it's so small, then the equation would simply just be the mass of B times gravity over mass of B. And that is equal to our acceleration. We can see that mass of B dividing by each other will cancel out, and that the acceleration would be close to G, which is what we said in part AI. So we can check off yes and explain. See that in our equation from earlier. If the mass of block A is much less than the mass of block B, then the mass of A can be considered negligible and approaches 0. Therefore, when we calculate acceleration, the equation simplifies to just G. This is what we predicted earlier. Moving on to part E. Briefly explain your reasoning by addressing y according to your equation. Oh wait, this part, let me apologize, was cut off from earlier, but it's basically the same thing. It approaches G as shown from our explanation if the mass of A is much less than mass of B. So this doesn't affect our answer, I just forgot to include it, so I'll apologize for that. Bear with me, it's our last part of the question number 2. This is longer, one of the longer problems, so it'll take some more time, but we're almost there, so let's finish strong. Part E. While the blocks are accelerating, the tension in the vertical position of the string is T1. Next, the pulley of the negligible mass is replaced with a second pulley whose mass is not negligible. Let's highlight this. This is key, not negligible. When the blocks are accelerating in this scenario, the tension in the vertical position of the string is T2. How do the two tensions compare to each other? Briefly explain your reasoning. So now the net force, which doesn't change, is equal to a greater net mass, which consists of mass of A plus mass of B plus the pulley, which we'll call the mass of P. And this is times the acceleration of the system. So net force doesn't change since there's no new forces acting on the system. So that means with the greater mass here, that means acceleration would have to decrease. So with the smaller acceleration in mind, let's take a look back at the forces from earlier. We know that the block, which is block of B, has a force of gravity downwards and a tension force up. And this is the tension force we're looking at in this scenario, T1 or T2. So we know that for block B, the force of gravity minus the tension force is equal to mass of B times the acceleration. So we know in the second instance, the acceleration is smaller. So if the acceleration is smaller, the net force is smaller. And that means f of g minus t has to be smaller as well. Since t is changing, in order for this to be smaller, in order for f of g minus t to be smaller, that means t would have to be greater or closer in value to f of g, so that when you subtract them, it results in a smaller number. So that means T2 would be greater than T1. So let's cross this off as our answer and explain in paragraph form. So with the addition of the mass of the pulley, the mass of the system is greater. With the same net force, that means the acceleration is smaller. When we look at the forces acting on block B, we see that tension would increase as the acceleration So with the addition of the mass of the pulley, the mass of the system is greater. With the same net force, that means acceleration of the system is smaller. When we look at the forces acting on block B, we see that tension would increase as the acceleration decreases. So this justifies our answer as T2 greater than T1. That would be it for the 2019 AP Physics 1 free response question number 2.